we're going to now talk about the introduction to what we call the derivative. And so we'll define that word very shortly. But let's again catch us up. So what have we talked about so far? Well, we've talked about the fact that calculus has two questions. The first question is, where is it going? And the two things that we have studied, limits and continuity, help us describe where a function is going. So now we're ready to start answering the question, how fast is it getting there? Now we've already talked about the answer to this question when we studied algebra. When we ask how fast something is going, we've talked about the fact that that is the slope, because slope is a rate of change. It is a speed or a rate. And so all of these things actually mean the same thing. So instead of using the word slope or rate of change, we could have used the word derivative. And so we're going to be looking at then, how can the slope of a function help us determine how fast something is going? So let's take a look at what we know about the slope or the derivative of a function. And let's start with the slope of a line. Okay? When we ask to find the slope of the line, what does that mean? Well, as I just mentioned, that it is the rate of change from one point to another. Now remember, with the rate of change, that there was a formula for that, and that is the change in y over the change in x, and we're probably used to this formula right here. y2 minus y1 over x2 minus x1. Now we need to take that a little more sophisticated. Remember, if this is, let me just draw an x and y axis here. If this right here is my a value, then to find the matching y value, I simply plug a into my function. So we can say the address of this point is x1 comma y1, or we could say the address of this point is a comma f of a. In other words, whatever we have in the x spot, so if I have x1 in the x spot, then I plug in f of x1 to find my y value. And that's going to be pretty important for us in the study of calculus, that we're not going to typically write y2 anymore, or y anything. We're going to write that as the function value at x equals 2. These two things are the same, but we're going to tend to that second description. So hopefully we can get very comfortable with that. So when we find the change in y over the change in x of a line, we are finding the slope. But the key is here that the slope is constant, that the speed of that line is constant, because it is a line and the slope never changes. No matter what 2 points we pick on that line, we are going to get the same answer. Well, so if life were that simple, if everything were a straight line, we would not need any more calculus. We would be done, because the slope of the line tells us how to find how fast something is going. So we need to realize that we are now going to be looking at things that don't travel at a constant speed. So think about your driving. When you drive to school, you don't drive exactly 52 miles an hour everywhere you go. Your speed is always changing. And what calculus allows us to do is look at the speed of objects at different times. So for example, if I am a doctor working with a cancer patient, and I'm looking at the speed of the growth of a tumor, then that's more important than the fact that I have a tumor. The tumor, if it's growing very, very slow, I can get a grasp on that. But if the tumor is growing very, very fast, then I've got problems. Or if the tumor changes its speed, so it was growing slow and now it's growing really fast, I've got to do something about that. And so a lot of times in medical research, we're looking not only at did something grow, did the bacteria grow, did the disease spread, but how fast did it spread. I can tell you for sure that when the swine flu was going around a few years ago, that the scientists or the medical people that were looking at that modeled how many cases of the swine flu there were after a given number of days, and they were not looking necessarily at the total number of cases as the issue as much as they were looking at how fast it spread, because that swine flu started off fairly slow, but then it started spreading very, very quickly to the point that they almost wanted to call it an epidemic. This is the area they were worried about, because if I draw that line in there, the steepness of that line is a lot different than the steepness of that line. And when that swine flu took off, they knew they had to do something about that. So now, we'll talk about the fact that not everything travels in a straight line. So if we have a curve, we're not going to get a constant speed. This segment in here has a different speed than that segment right there, okay, even though they're both on the same function. So at different times on our graph, our speed will have different values. So if we imagine that this is our graph and this is units of time, and this could be distance, it could be number of bacteria present in a culture, it could be dollars if we're talking about profit, but over time, how is that changing? Well, from the first A to B here on the left, maybe I'll make them A1, B1, we're having a pretty drastic increase. But from B2 to A2, we're having a decrease, and it's a little bit slower. And so we're going to be talking about that. All right, so a couple important things to remember. Number one, that X and Y stand for something, okay? Typically, the X-axis is going to stand for time, the Y, or a unit of time. The Y-axis is going to stand for a quantity of something, whether it's miles, whether it's dollars, whether it's bacteria in a culture. The slope of the curve in that area is the speed at which the item is moving or changing. So as I mentioned, from A1 to B1, this area right here has a much faster change than from B2 to A2. That one's slowing down and it's going negative. So if I'm talking about money, things aren't going good on the later half. If I'm talking about the growth of bacteria, I'm gaining some ground. It's first growing really fast, but somehow I'm able to control it. So the slope is going to help us understand the speed. All right, so that's where we're heading in calculus, is that we want to be able to keep track of how things are speeding up and how they are slowing down. Now, how are we going to find the slope of the curve? Well, you might already have an idea here that we can do a pretty good job at estimating the slope of the curve. And when we estimate the slope, we are actually finding the slope of a line. We know how to find the slope of a line. We just need 2 points. And so to find the slope, if I wanted to know what my speed was right here at A, then what I can do is pick 2 points that are fairly close to A, and I can connect them. Now, my connecting line doesn't match my curve exactly, thus the estimate. The slope of the secant line, and a secant line, if you remember, is a line that touches the curve at 2 points. The secant of a circle cuts through the circle at 2 points. So the secant line doesn't look like the curve exactly, but it's going to give me a good estimate at what's happening in that area. It's going to give me the average rate of change. So if I go from x1 to x2, then it's going to tell me on average what was my rate of change. So if I'm driving, I might speed up, slow down, but when the trip is all over, did I average 40 miles an hour or did I average 60 miles an hour? And actually in the state of Maine, the troopers will often sit, the state troopers will often sit right at the exit points to pay your toll, because the turnpike up there is a toll booth. And so if you, we'll go to Visit Maine here, and I get on the toll booth here, and I pick up a ticket. And the ticket has a certain time on it. And let's say I go up here to exit 100. Okay? Which means I've traveled 100 miles. And on this ticket is a time that says 2:00 p.m. And when I get off at exit 100, it says 3:00 p.m. Now, the trooper never saw me driving a certain speed, but he can prove that if I went from 2 p.m. to 3 p.m. and I went 100 miles, that at some point during that drive I hit exactly 100. I might have actually hit 163 miles an hour. He can't prove that, but he can prove using calculus that I actually went 100 miles an hour for a split second. Because I might have driven faster, but then that means at times I drove slower. On average, I averaged 100 miles an hour. He writes me a ticket without ever getting me with a radar gun. And so there are many, many times that tickets are not, I haven't gotten one, but that tickets are given on the turnpike in Maine because of that. So let's find this. Let me just pick that x is 4 and that x2 is 9. So remember that to find the slope, we do the function value of x2 minus function value of x1. In other words, the y values are subtracted. And to find those y values, we simply have to plug into the function square root of x. So the square root of 4 is 2, and the square root of 9 is 3. So our slope is 3 minus 2 over 9 minus 4, which is 1/5. So the slope of that line is 1/5. But that is only an estimate. And so the question is, can we get it closer? Can I get the, let me switch colors here so I can draw another line. Can I get the estimate to be better? Well, to make that estimate better, what do I want to have happen? I want that line to be closer to my curve. So what if I pick this point right here and this point right here, and I connect them? And now that green line is even closer. So maybe now this would be at 5. Maybe this point is actually at 6, and maybe this is at 8. Okay, so to find the slope of the green line, we're going to do f of 8, so we're going to plug in 8, minus f of 5, all over 8 minus 5. So the easy part is the 3 on the bottom. So we need to estimate the square root of 8, which is 2.83. And this is going to be an estimate because these aren't exact. And the square root of 5, which is 2.23. And so we subtract that. We get 0.6 divided by 3, which equals 0.2, which equals 1/5. Now, not a great example, is it? But I'm glad that happened. Why did we get 1/5? but we got 1/5 before, and we said that wasn't great, and we wanted it to get closer. Well, that's because I rounded my numbers. So what I'm actually going to do is go back to my 2.83 and make that 2.8284. And the other one will make 2.23607. Okay, 23607. Alright, so now when I do 2.8284 minus 2.23607 and divide that by 3, so that instead of being 0.6 becomes 0.5923, and we divide that by 3, what we really get is 0.197, which is a little bit less than 1/5. And that's a better answer. It's more exact. So when we used 4 and 9, we got 1/5. When we used 5 and 8, my slope is a little less than 0.2, which is about 1.97. And if we were to use 5.5 and 7, we might get that to be something like 1.91 or something slightly. So it looks like the slope of that is approximately 0.19 or 0.197. Okay. So the idea is we can estimate the slope of any curve if we simply pick 2 points, and those 2 points will be the points of the secant line, and that is your average rate of change. So remember my example about the Maine Turnpike? I might have been more than 0.197 at some point, less than 0.197 at some point, but it averaged out to 0.197. So then the question is, how could we find a better estimate? So let's take a look at that. Okay, so to find the slope, we need 2 points. And to find those 2 points, we just pick 2 points. So if this were again my A, and I'm trying to find the slope around A. So I really want to know exactly how fast something was happening at time A. Alright? Well, first we picked points here and here. So we picked from x1 to x2. And that gave us a pretty good line. Then we moved them in. So make little x's. And we called these x3 to x4. Okay. What's happening to my points? Well, how could I make that even better? Well, the closer my points get to the real thing, the closer that line no longer looks like a secant, but starts to resemble what we call a tangent line. And a tangent line touches my graph only at one point, whereas a secant line touches us at 2. So we want our 2 points to be so close together, so maybe x5 and x6, for those to be so close together that they're so close together they almost look like they are touching. So we want this distance right here, which is the distance between the 2 points, to get very, very tiny. So we want the distance between 2 points to get very, very tiny. Okay? We call that distance h. H is the horizontal distance between 2 points. So we want h to get tiny. What do we mean by tiny? We want h to get so tiny that it gets very approaches or gets very, very close to 0. Where are we going with this? So we want to know what's happening to our function to our slope. What's happening to our slope as h gets very, very close to 0. That's an important sentence. Let me write it. What's happening to our slope function? To our slope function. So now we're talking about slope as the function because we want to know what's happening to the speed. So let's talk about the speed, which is the slope, as h goes to 0. Alright, well, let's put that into words. I'm going to leave the front blank for a minute, and that is our slope function, which is f of x2 minus f of x1, and those x1 and x2's can be any number, so f of x5 minus f of x6 over x2 minus x1. That's our slope function. So what is happening to that function as h gets closer to 0? To answer that question, we take the limit as h goes to 0. So here's what that last line says right there. What is happening to our slope function as the points are closer? Okay. And when those points get so close that we really think we're just looking at that one point, instead of it being the average rate of change, it becomes the instantaneous rate of change. Okay, so average rate of change is when you have a secant line with 2 points on the end. You find the slope between those 2 points. Instantaneous rate of change is when you have the 2 points so close together that it looks like they're touching, so it looks like you're really only asking what is the slope at one point, and that is the slope that is at that exact point, which is the instantaneous rate of change. Now, here's one little issue. We have h in our limit, but we don't have h anywhere in our function, so we need to fix that. And so it just takes a little thought. So, oh, that's an h. Isn't that a bad h? Let's see if I can fix that. So how can we fix this so we have h? Okay, here's how. Remember, we called the distance between the 2 points h. So the distance x2 minus x1, that distance is h. Okay. Now, how about the y values? Well, we got to get rid of 2 letters here and see if we can get it down to one with an h. I'm going to switch to a green pen so you can look for that color on the screen. Over here, instead of calling this x5, I'm going to call it a. That's one of our points. And then I go h units to the right, and my next point, I'm not going to call it b, but think about it. If you start at 2 and I tell you I want you to go 3 units to the right, we don't have to write 5. We could write 2 plus 3. So you started at 2, you went 3 units to the right. So if I started at a, my next point would be a plus h. So wherever I started, maybe I should go out here to x1. If we called x1 a, and I go h units across, my other point is a plus h. So when I go to find the function values, I'm going to plug a in for that one and a plus h for that one. So this would be a plus h instead of x2, and x1 we're just calling a. So again, h is the distance between a and the other point. So if I know where a is, I can add h to it to find my other point. This formula in the green box is the beginning of the idea of the derivative, and it represents the instantaneous rate of at a point, which is another way of saying the slope at that point, or the rate of change at that point, or the derivative of that function at that point. And there's a symbol for that that we'll see later, but it's just F with a little tick mark, which means derivative. What's the difference between instantaneous rate and derivative? Just what form your answer's in. Instantaneous rate of change is typically a number. You're finding the instantaneous rate of change. The derivative is a formula that gives you that answer, and so we'll see that a lot. So let me summarize this for us. Let me get to the next screen. And I'm sorry that I wrote over those, but I think you have the slides, so hopefully you put the notes in and amongst those slides. There's the symbol, by the way, for derivative, is that little f prime. Okay, so where did we start and how did it get us? I don't know if you remember something called the difference quotient. The difference quotient actually is kind of the more formal way of saying the slope. So we often called this the slope, and that was when we had 2 points, column A and B, and we had the y values minus the x values. Okay, that was for a line. So now we start looking at how does this apply to a curve, and what we realize is that we can't find the slope of a curve, but we can find the slope of its secant line, and we can estimate that. So that turned into the average rate of change, or the average velocity, which is that slope of the secant line, which is this formula right here. Remembering that h is the distance from A to B. So this thing right here, don't panic about that, because what is A minus A? It's h. So that's just telling you the distance from A to B is h, and that's the horizontal distance. So then we take the average rate of change and we let h get very, very small. Once h gets so close to 0 we can't tell it apart, the average rate of change becomes the instantaneous rate of change. But to do that, we have to let h get so small that we have to look at the limit. And this becomes instantaneous, and the secant line becomes the tangent line. So instantaneous goes with tangent, average rate goes with secant. It all comes from the difference quotient, or the formula for slope. So then we take that into actually dealing with equations versus numbers. So up to this point we would have had a function, we would have plugged in numbers, we would have found the actual slope. But now when we want to find the formula for a slope, we're actually looking for the derivative of a function. So notice now, instead of plugging in for a and or b, we have our functions f of x. And this right here actually gives us the formula for the slope of the curve at any point. So it gives us a little formula, whereas this finds the slope at a point. But they're the same exact thing, it's just whether you're using all numbers or not. Okay, so kind of summing up on the next slide, I'll kind of do these two together, but so, why do we care about this thing called the derivative? Well, that is the equation that gives us the speed. So if I want to know what the speed of an object is, I want to have an equation for that. And it's helping us understand how fast things are traveling. Okay. Don't forget that derivative does mean slope. Okay. We don't really want to use the word slope because the slope is the constant speed of a line. And so to say the slope of a curve really isn't kosher. Okay. Now let's talk though about when does a function have a derivative or when does it not. So when does something have a slope and when does it not? Well, we might not have a slope. If we think of a line, we don't have a slope when the tangent line is vertical. The slope is undefined. So if ever our tangent line, or we don't have a slope at all of a line when it's vertical. So if our tangent line, if I had a curve, let me see if I can get one. There's actually something like that. It's not exactly vertical, but if this tangent line ever looks like it's becoming vertical, that little piece, then we might not have a slope. Also, if our function doesn't take up what's called a positioning stance, if it starts to look like a teeter-totter. And we will actually talk about that in a little while, but I just wanted to mention that functions do not always have derivatives, and functions do not always have points, or will often have points that don't have derivatives. So you can find the slope of most of the curve, but maybe not at one. So let's do one example, and then we will stop there for this series and then pick up in the next lesson. Let's use the function f of x equals x squared, and let's find the slope of that at different points. So if we graph f of x equals x squared, we're looking at a parabola. And we can talk about, what would our slope be here at -4? What would our slope be here at 0? What would our slope be here at 1? Or up here at 6? And we wanted to find the slope of different areas there. Well, again, one way to find the slope is I could pick 2 points and draw myself a secant line and then just use change in y over change in x. But let's actually use the derivative to find the slope of this curve at a bunch of points. So first, let's find the derivative. And so the derivative is where we take the limit as h goes to 0 of f of x plus h minus f of x all over h. Now remember the difference quotient. That's exactly where this is coming from. We take the function, and wherever we see an x, we add an h. So my function is x squared. In place of the x, I put x plus h, and I square it. Minus f of x is x squared all over h. So now I need to clean this up, and so the limit as h goes to 0, I got to multiply all that out, so I have to do x plus h times x plus h is what I'm getting ready to do. So that gives me x squared plus 2xh plus h squared minus x squared all over h. And remember, when we're cleaning up, we can divide everything by h. So the limit as h goes to 0 of the x squared, subtract 2xh divided by h is 2x plus h. Now take my limit, and the limit as h goes to 0 is 2x. So we would write this as f prime of x. This is the derivative, and this gives me a formula for the slope. This is a formula for the slope, or the rate of change of the curve at any point. So instead of me picking 2 points really close together, like instead of for 0 picking this point and this point, like picking -1/2 and 1/2 and drawing this line right here and finding the 2 points and plugging them into y minus y over x minus x, I can just say f prime of 0 is asking me what is the slope of the curve at 0, and in fact, if we do 2 times 0, we get 0. The tangent line at that point is horizontal. The slope of that tangent line is 0. Okay. How about at -4? So I want to know the slope of the line at -4. So I'm going to write up, remember that the derivative we just found was 2x. So we plug in 2 times -4, and my slope is -8. So the slope of that tangent line is -8. And how about at 1? That would just be 2 times 1 is 2. So the slope of that tangent line is 2. And at 6, the slope of that tangent line is 2 times 6, which is 12. So I could have, for every single one of those slopes, found 2 points and use the slope formula, or I can take the derivative, get a formula for the slope, and then plug in any point I want to find the slope at that curve. And so hopefully these slopes make sense. -8 is fairly steep, coming in the negative. It flattens out at 0, so it has a slope of 0. And then it starts having a positive slope of 2, starts getting steeper with a slope of 12. Okay. So when we want, if I just wanted the slope at one point, then there might be an easier way. But if I want, I could just plug in the numbers. Like if I had wanted only at 2, if I had wanted the slope at x equals 2, then right here I could have plugged a 2 in and a 2 in. So instead of having x plus h, I could have had 2 plus h and 2 squared, and then I would have worked it out, and I would have come down to 4 plus h, taken the limit as h goes to 0, and I would have gotten 4. But if I want the slopes of many points, then finding that equation is going to be more helpful, because now I can plug in multiple times. Okay, so the difference quotient, or the instantaneous rate of change, is when you're just dealing with one point, whereas the derivative gives you the formula that works for the entire curve. So as you start on your work in this, be thinking about what it means to have a slope, and how to find it and what the equation represents. And we will pick this up more, talk a little bit more about when do you not have a derivative, when can you not use a formula, and also we will take a look at what if what can we do more about this tangent line. So that's what we'll finish up in part 2 of the intro of derivative next week. So until next time.